Good evening, students. I hope you are able to hear me.
Yes, sir.
So also confirm if you are able to see my screen.
Yes, sir.
Yes, sir.
Okay. So let's start it in 2 minutes. So last class we were discussing the characteristics of photoelectric effect. Right? We saw 2 characteristics, out of which one of the characteristic was effect of intensity of incident radiation on photoelectric effect. This we saw, and I told you it will be a straight line. So that is when you increase the intensity, the photoelectric current will also increase along with it. So we already saw this. Similarly, we saw the second one also. We saw what is the effect of potential difference on photoelectric current. That also we saw. So I explained it separately, right? Okay, I've deleted the document. Yeah, it is here. So do you guys remember this graph? I told you that when we vary the potential difference with respect to time by keeping the intensity and frequency constant, when you keep the intensity and frequency constant and when you vary the potential difference, that is the potential of the anode, you give positive potential to observe that the graph will start from a non-zero value and it will increase in such a way that the current will get saturated after a certain point. So after a certain potential, the value of current will get saturated. Whereas in the reverse direction, the current will decrease and it becomes zero at a particular value, which is called as the stopping potential. So I explained what is stopping potential also. It is the amount of reverse potential, that is the negative potential that needs to be given to the anode to ensure that the electrons do not reach. So with the help of that, we will be able to find out what is the maximum kinetic energy of the electrons by using the work energy theorem. So this also we discussed in the previous class. So EV naught is equal to half m into V max square, right? So this is one of the important equations. Have this in your mind. There are very few formulae in this chapter, out of which this is one of them. Okay. So is there any doubt in these 2 points? Okay. I assume there is no doubt. So one important point to be noted from here is when the light is of a given frequency, that is when the frequency of the incident radiation is fixed, then the stopping potential is independent of its intensity. Last class I explained it, that the stopping potential does not depend on the intensity of the light that you use. Whatever is going to be the intensity, it is going to be a constant, provided the frequency is constant. Okay. Just a minute. Okay. Now listen. So the third property that we are going to see is effect of frequency of incident radiation on stopping potential. Okay. This is a very, very simple point. So when we say effect of frequency, our expectation will be in such a way that frequency is taken on x-axis. No. The frequency is not taken on x-axis. Rather, you will be considering the same anode potential on the x-axis where you will be given a positive value and a negative value. But here, we are going to keep the intensity of the incident radiation fixed. Okay. So read out, keeping the photosensitive plate and the intensity of the incident radiation a constant, the effect of frequency of the incident radiation on stopping potential is studied. Okay. So the figure shows the variation of photoelectric current with applied potential difference V for three different frequencies. See here, there are three frequencies, nu1, nu2 and nu3 that are applied, where nu1 is less than nu2 is less than nu3. Okay. So if you take only one particular graph, that is when you try to observe the variation. Say I'm drawing a separate graph, observe. So when you apply positive potential, since the intensity of light is non-zero, the photoelectric current will also be non-zero. So it will again start something similar to what happened in the previous case. Then it will go high. Then a saturation value is attained. Similarly, when you apply the retarding potential, what will happen is the photoelectric current will decrease and you will have a particular stopping potential. Now, what we are going to do is we are going to increase the frequency by keeping the intensity constant. Intensity means same amount of brightness. See, for example, here we use green light, here we are going to use red light. So the frequency is changed. Okay. I'm sorry, it's the reverse actually, because the wavelengths are reversed, right? So try to understand that we are going to use two different colors. That is the meaning of frequency being changed. When frequency is changed, what will happen is when you use a slightly higher frequency, the photoelectric current will also be slightly high compared to the initial value. Again, it will increase with the anode potential, then it will get saturated. Here, what is going to happen is the saturation current will be in such a way that it is independent of the frequency. Whereas, when you apply the retarding potential, it is observed that the stopping potential in all the cases are different. That is a very, very important point. Means the stopping potential will vary in such a way that for higher the frequency, higher is going to be the stopping potential. Please make a note of it. So, higher frequency, higher value of stopping potential. Okay. It is found that the higher the frequency of the incident radiation, higher is the value of the stopping potential. Okay. So, the reason for this to happen is, according to Planck's equation, we know that E is equal to h nu. Right. So the energy of the light that is incident on the surface is directly proportional to the frequency of the light that is being used. When this is clear, we can understand one more important point. Then this will in turn lead to maximum kinetic energy. So higher is the frequency of the incident radiation, then the kinetic energy attained by the electrons will be maximum. So higher is the value of kinetic energy, then higher is the value of stopping potential. So this is how the flow will go. Okay. Please make a note of it. And one important point that comes is, it is concluded from the graph that the maximum kinetic energy of the photoelectron varies linearly with frequency of incident radiation, but is independent of its intensity. How much ever is the intensity of the light that is going to fall on the surface, the maximum kinetic energy is decided only by the frequency of the incident radiation. Is there any doubt?
No.
Okay. So now listen. So this graph, I will explain it again, okay? Hold this graph. So till here, have all the points in your mind. After that, I'll come how this graph is actually drawn. So based on all the experimental observations, that we have seen till now, few laws of photoelectric emission are designed. Let's see what are the laws that are designed. So for a given photosensitive material, there is a minimum frequency that is required. What is the name of that minimum frequency? That's called threshold frequency, below which you cannot observe the emission of photoelectrons, however great the intensity may be. So how much ever intense light you are going to use, unless the condition of this minimum frequency, that is the threshold frequency, is satisfied, you cannot eject any photoelectron out of the surface. Second, for a given photosensitive material, the photoelectric current is directly proportional to the intensity. That is the point we saw in effect of intensity. Is directly proportional to the effect of intensity of the incident radiation, provided the frequency is greater than the threshold frequency. But the vice versa will not happen. If you have greater intensity, but the frequency is less than threshold frequency, no photoelectric emission will take place. Okay. This is the second important point. Third, the photoelectric emission is instantaneous process. This is a very, very important point. Have it in your mind. It is an instantaneous process. That is, there is no time lag between the incidence of radiation and the emission of photoelectrons. So as soon as the electrons are incident on the metal surface, provided they have threshold, provided it has threshold frequency, the electrons are emitted out of the surface instantaneously. It is an instantaneous process. So the time gap is less than 10 power minus 9 seconds. That is 1 nanosecond. And the last important law is the maximum kinetic energy of photoelectrons is directly proportional to the frequency. This I have explained. Frequency of incident radiation, but it is independent of its intensity. Okay. So these are all the laws of photoelectric emission. Can just go through them. If there is any doubt, let me know.
No doubts.
So we'll proceed to the next topic. So now we will see the topic of light waves and photons. You would have heard this word photons. Okay. So based on all these observations, right? One important point we need to understand is for the explanation of photoelectric effect, we can only use the particle nature of light. We cannot use the wave nature of light, because we will see at the end why wave theory actually failed to explain photoelectric effect. Okay. Then came the concept of this photons. So before that, let's read out what exactly gave the origin of it. So the electromagnetic theory of light was proposed by Maxwell, which couldn't explain the photoelectric effect. This we know. Secondly, we know that the Planck's quantum theory successfully explained photoelectric effect, because according to Planck's quantum theory, light is emitted in the form of, this is the important point, form of discrete packets of energy called as photons. So if you ask me what are photons, photon is nothing but a bundle of light energy. Okay, it is a discrete packet of energy, and the energy of each photon according to Max Planck is E is equal to h nu. This expression you already know, where h is called as the Planck's constant, which is 6.626 into 10 power minus 34 joule second. Okay. So the next important point is, the question is photon a particle or a wave? Photon is neither a particle nor a wave. When you explain the phenomenon like interference, diffraction, and polarization, photon behaves like a wave. Whereas when you explain the phenomenon like emission, absorption, and interaction with matter, that is a photoelectric effect, photon behaves like a particle. So photon has dual nature, but photon is nothing but a packet of light energy. Okay, this is just an introduction of the term photon. So going forward, you need to understand that when we speak about photoelectric effect, we are trying to speak about the light in the form of photons, where in that case, the light is behaving like a particle. Are you guys clear with this?
Yes, sir.
Yes, sir.
Okay, it's a simple point. So let's go to the next concept. So Einstein was a person to come up with some mathematical equations for this photoelectric effect. So that's why it's called as Einstein's photoelectric equation. So what he did is, he applied the quantum theory of radiation to photoelectric effect. So according to him, okay, the emission of photoelectron is the result of interaction between, see, this is an important word. It is an interaction between whom? It is an interaction between single photon. Remember, how much is the energy possessed by a single photon? The energy of each photon is h nu. Have this in your mind. So interaction between a single photon of the incident radiation and the electron in the metal. So let me explain this concept. So you have, let's say you have a photosensitive plate C. Okay, you have a photosensitive plate C. There is one photon of energy, how much value? H nu, which is incident on this photosensitive plate. So what is going to happen? First thing, the electron which is in the outermost orbit needs to acquire energy so that it needs to acquire the minimum amount of energy to break the electrostatic bond between whom? Between itself and the nucleus and come out. Okay. So once it comes out, what is the next step? Let's say it has come out. So what is the next step that we need to ensure? After it comes out, it should have sufficient amount of energy within itself so that it escapes further from the pull of the nucleus. Right? So what is the photon doing? So that one photon, when it is falling on the surface, first is it is supplying the minimum energy required by the electron to come out of the metal surface, which is technically called as the work function. So I will write down the equation. The energy of single photon is able to overcome the work function, and once it's a plus, it should also acquire some kinetic energy, which is given by half mv square. Right? So that's what is given here. See. So according to Einstein, the emission of photoelectron is a result of interaction between single photon of the incident radiation and an electron in the metal. So when a photon of energy h nu is incident on the metal surface, its energy is used up in two ways. Not the second point, this is the second point. So part of the energy of the photon is used in extracting the metal from the surface of the metal, since the electrons and metal are bound to the nucleus. That is what is work function. Okay. And the second is the remaining energy of the photon is used to impart kinetic energy to the liberated electron. So h nu will be equal to W plus half mv square. So this is not the equation proposed by you. Next came an important observation. If the electron that is coming out, if it does not lose any of its energy by undergoing internal collisions, okay, the electron is going to come out. It should be ensured that the electron, if it doesn't undergo any of the internal collision as it escapes from the metal, then the entire energy, what is the entire energy? It is h nu minus w naught, will get completely converted to the maximum kinetic energy, will be exhibited as the kinetic energy of the electron. That is, h nu minus w naught will represent the maximum kinetic energy of the ejected photoelectron. Okay, if that is the case, then the small change that we need to do in mv square is it will become m into v max square, because mass of the electron is not going to change, but its velocity can be taken to the maximum value. So this h nu is equal to w naught plus half m v max square is what is called as the Einstein's photoelectric equation, and this is the important formula that we are going to use to solve the problem. Okay. So it's a very, very, very simple equation, and it is easy to understand also. It's just like energy conversions that are happening. I can even say it is energy conservation. One energy is getting converted to two other forms of energy. Okay. And one important point to be noted here is, till now we understood that work function is the minimum energy required for the electron to escape. But work function, if you have to give a formula, it is written as h into nu naught, where the nu naught is called as the threshold frequency. Okay. So that's the point given here. When the frequency nu of the incident radiation is equal to the threshold frequency of the internal surface, kinetic energy of the electron is zero. Thus h nu naught is equal to that. So other way to understand it, you can directly write it as h nu naught, where nu naught is the threshold frequency. Threshold means minimum. There is nothing like threshold wavelength. Okay. So I just want to explain one important point which is not there here. So nu naught can be written as c by lambda. So when you call nu naught as the threshold frequency, Threshold frequency is minimum value, means this lambda naught is the maximum wavelength. You should not call it as threshold wavelength. Why? Because threshold means minimum. Okay. So if you take this W naught and substitute it here, then you will get the equation as H nu is equal to W. So I write the equation again, half m into B max square. So H nu will be equal to H nu naught plus half m B max square. So rearrange the equation, you will get the required expression. Clear? Is it clear? Is there any doubt?
No doubt. Sir,
Tell me.
can you show the previous page? Yes, sir. Thank you.
Okay. So from here, we are going to do some other manipulation. So experimental verification of Einstein's photoelectric equation. That is, the theory proposed by him is H nu is equal to H nu naught plus half into B max square. That is H. Okay, I'll leave it as it is. Okay. So this is the theory proposed by him. But experiment told us that EV naught is equal to half mb max square. We found it from the second experiment. So in the place of half mb max square, if you take EV naught and substitute, so don't get confused between V naught and nu naught. H nu will be equal to H nu naught plus E into V. Okay. So from this, what we can do is EV naught will be equal to H nu minus H nu naught. So V naught will be equal to H divided by E into nu minus H divided by E into nu naught. If you get confused with nu naught and V naught, I would suggest you to write it as F. Instead of nu, you can write it as HF is equal to HF naught plus EV naught. This is also accepted. Where F is the frequency of the light, F naught is the threshold frequency, V naught is stopping potential. It's up to you. Okay. Now listen. So V naught is equal to H by E into nu naught minus H by E into H by E into nu minus H by E into nu naught. So what was it? V naught is equal to okay. So we observe the graph between the stopping potential and the frequency. So stopping potential is taken on y-axis. Is it not of the form y is equal to mx plus c? So y is equal to mx plus c is a straight line with slope as m and the y-intercept to be plus c. So here what is going to happen is when you put nu is equal to 0. Okay, when you put nu is equal to 0, what is going to happen? So, upside. You will get the y coordinate. So, what is the y coordinate you are going to get? What is the y coordinate you will get for this?
Minus
So when you
h
put
by e.
yes, minus h by e, is it all?
Mu naught.
Ah. So h by e into nu naught is the negative c intercept. So when you plot the graph, okay. Similarly, when you put v naught is equal to 0, you will get the y coordinate. Sorry, x coordinate. So when you put v naught is equal to 0, you will get h by e into nu is equal to h by e into nu naught. H by will get cancelled. Nu is equal to nu naught. So that's the threshold frequency. So this is the important point. I didn't explain it then. See, now I will connect all the dots. See, if the frequency of the incident radiation is plotted against the corresponding stopping potential, a straight line is obtained as shown in the figure. So that's what they've given it here. But the reason for that comes mathematically like this. So from this graph, it is found that at frequency nu naught, the value of stopping potential is 0. This frequency is known as the threshold frequency of the photometal used. So this is the threshold frequency. Similarly, the photoelectric effect occurs above this frequency and ceases below it. Therefore, threshold frequency is defined as the minimum frequency of incident radiation below which photoelectric emission is not possible completely. So threshold frequency is obviously different for different metals. And this is another important graph for you to remember. So is everyone clear with how you got this graph?
Sir, can you explain that graph again, sir?
I have applied y is equal to mx plus c. This you understood? Huh?
Yes, sir.
So this is y, this is m, nu is x, c is this thing. What is the meaning of y is equal to mx plus c? So y is equal to mx plus c is a graph like this. There's x-axis, there's y-axis. So you will get a graph like this, where this point is 0, c, and this point will be what? Minus c by m, 0. How did you get them? So listen, to get the red color point, you need to put x is equal to 0. So when you substitute x is equal to 0, you will get y is equal to c. That is why the point is 0, c. Similarly, for you to get the green color point, you need to put y is equal to 0. When you put y is equal to 0, x is equal to minus c by m. So if I use the same logic, then the mathematical equation that I had in my hand is v naught is equal to h by e into nu naught minus h by e into mu, right? Nu minus h by e into nu naught. So v naught is y-axis. This is x-axis. This is m, and this is c. Okay. So to get the value of c, what you need to do? You need to put x is equal to 0. X is equal to 0 is this thing. So when you put x is equal to 0, you will get the y-intercept here. So the graph will go like this. Similarly, when you want this coordinate, when you want the red color coordinate, then what are you supposed to put 0? You yourself tell me.
Y equal to 0.
Means v naught should be 0. When you put v naught is equal to 0, what will happen? H by e into nu will be equal to h by e into nu naught. H by e will get cancelled. Nu is equal to nu naught. So what will be the coordinates of this point? Nu naught,
Mu
comma
naught
0.
comma 0.
Now the graph will go like this. It will be a straight line. That is how you got. Provided x-axis is frequency and this is stopping potential. Now you understood?
Yes, sir.
So this is the graph. So with this, we have completed the first part of the chapter. So what is the name of the chapter? Dual nature of radiation and matter. I put it in reverse. So dual nature of radiation. Radiation means here we are trying to talk about light. So light has dual nature and we have explained it. Last chapter we explained it with the wave theory. In this chapter we explained it using the particle theory for photoelectric emission. So the question arises like this. When light has wave nature and particle nature, right? When light can behave like a particle, the question that arises the vice versa. That is, will a particle be able to behave like a wave? Okay. Will there be anything like wave properties associated to a particle? That is the meaning of dual nature of matter. Okay. Because particle by default will have particle nature. Will it also have wave nature is a question that has arisen, because in physics what happens is if some theory works out right, then the symmetry also should work. For example, when you can generate, see, actually we didn't discuss a concept called as displacement current, but anyways it is not important. I'll just give you the outline, you understand. So the fourth chapter, if you see, it says magnetic effects of current. What happened there? What was the main observation of magnetic effects of current? From current, whenever there is a current carrying conductor present, what is present around according to that chapter?
Magnetic field.
You can sense magnetic field because you place a compass, it is going to show some reflection. That's what they told. Now the next question arises, that is, so, and one more important point. Okay, so something like this. And in the same chapter, we saw using magnetic field, we can generate current also. That is symmetry. One more thing is Faraday's law of electromagnetic induction. So what does Faraday's law of electromagnetic induction state? By changing magnetic flux, you can generate
Current.
EMF. So you can generate EMF. So EMF is related to electric field, accepted? Because EMF means what? Potential difference. We know that potential difference and electric field are related. How are they related? E is equal to minus dV by dr. So electric field is a negative of potential gradient. So potential and electric field are related. So what I'm trying to say here is, if you are able to change magnetic flux, you are able to generate electric field. Then as I told you, physics will follow symmetry. Would the reverse also be possible? That is, if you change electric field, will you be able to produce magnetic? That is, if you are able to change electric flux, will you be able to generate magnetic field? And the answer to that is yes. Okay, that's what was actually explained in the concept of displacement current. Okay, in a similar way, if you observe, when light is having particle nature, will particle have wave nature is a question. So, based on that question only, the first type of wave that we are going to see is matter waves. Okay. So, as I told you in the beginning of this chapter, this was a question which was raised by scientist de Broglie. However, you are comfortable, you want me to pronounce it as de Broglie, I'll do it. The actual way of pronouncing is de Broglie. Okay. I want you to understand the concept. So listen, the radiant energy, that is light, has dual aspects of particle and wave. Hence, a natural question arises, if radiation has dual nature, why not matter? That's what I was trying to say, because nature will follow symmetry. So in 1924, what happened? This French physicist de Broglie put forward the bold hypothesis that moving particles should possess wave-like particles under suitable conditions. So he reasoned this idea from the fact that nature is symmetrical, and hence the basic physical entities, that is matter and energy, should have a symmetrical characteristics. Okay, characters. If radiation shows dual aspects, so should matter. That is what we are going to discuss. So from going forward, what we are going to discuss about is how will you relate the energy and matter is related to mass. And energy we mainly speak for wave. So we are going to create a symmetry between them. That's what we are going to discuss going forward. This also you would have actually learned. So let me explain what it is. So you would have heard this, right? De Broglie's wavelength of matter waves. So what he did is, listen to it carefully. So he came up with an equation by relating the energy equations of Planck and the energy equation proposed by Einstein. Okay. So what was the energy equation proposed by Planck? He told E is equal to h nu, where h nu is the energy of each photon. Now, what is the energy equation proposed by Einstein? It is mc square. It is called as energy mass equivalence. Okay, it's called as energy mass equivalence. So, when both are speaking about the energy, then can I write h nu is equal to mc square? And where nu is equal to c divided by lambda, this is equal to mc square. C and c will get cancelled. From this, lambda will be equal to h divided by mc. Okay. So when lambda is equal to h divided by mc, now comes the question. So if the particle is moving with the speed v, then c can be replaced with v. Then we can write lambda is equal to h divided by mv. What is this? You would have seen this equation. This is what is called as de Broglie's wavelength. Okay. So the manipulations that we can do from here is lambda is equal to h divided by mv is one way of writing, or lambda h divided by what is m into v, guys?
Momentum.
Linear momentum.
A moment.
Or this can also be written as h divided by, see, whenever a particle has mass and velocity associated with it, okay, whenever it has mass and velocity associated, along with linear momentum, you can also define its kinetic energy in such a way that kinetic energy is half mv square and linear momentum is mv. So if you square on both sides, you will get m square v square. Then p square divided by 2m will be equal to kinetic energy. So this is another important relation. So P will be equal to root of 2m into K. So in the place of P, I can also replace it and write it as root of 2m into K. So all these are the equations of de Broglie's wavelength. So what did he do? It's a very simple aspect that he followed. What did he do? He equated the Planck's equation of energy to Einstein's equation of energy. Einstein's equation speaks about mass energy equivalence. Planck's equation speaks about, so I put it in the bracket C. Planck speaks about wave, Einstein speaks about particle. So when these two energies are equated, then you get the wavelength output, and that is this expression. Please make a note of it.
So can you show the previous page?
You want me to show this page?
Yes.
Oh. Okay.
Yes, sir.
Okay. Next is, how will you apply this de Broglie's wavelength? How will you calculate the de Broglie's wavelength of an electron? Okay. Because electron is a particle, how can you relate this the particle nature of electron to the matter waves is the question. Okay. So listen, when you have an electron of mass m and charge e that is accelerated through a potential difference v, then EV is the energy which is equivalent to the kinetic energy, because listen, if there is a potential difference existing, let's say V, and you have an electron, the electron gets accelerated in it with a potential energy of how much value? EV. And this EV is what is getting converted to the kinetic energy. Right? That is, the electrostatic potential energy is giving the necessary kinetic energy. So when you write half mv square is equal to E into V, so what did we discuss? The previous equation is lambda is equal to h divided by m into V. So h divided by m into, in the place of V, what can I write? EV is equal to half mv square, guys. This is capital V. Okay. So what is the value of velocity? It will be root of 2m into E into V, the whole divided by m. So this will be square root of 2 EV divided by M. Right? So take this and substitute it here. Then what will you get? Lambda will be equal to h divided by root of 2e into v, the whole divided by m. Okay. So there is one such expression where, so there's the equation here. And something.
Sir, you missed the mass.
Yeah. So I think I wrote it wrong. Just a minute. So V will be equal to root of 2m into EV. So lambda will be equal to h divided. Oh, it is 2 by it. The square root of 2 EV, the whole divided by n. Yes. So when you multiply this with, so lambda will be equal to h by m into, I'll take this velocity and substitute it here, which will be root of 2 EV divided by m. So what will you get? It will be h divided by root of 2m into EV. Okay. So there is the wavelength of what? There is a de Broglie's wavelength of an electron. Okay, h divided by root of 2m into EV. So if you substitute the value of h as 6.626 into 10 power minus 34, mass of the electron is 9.1 into 10 power minus 31 kilogram. Charge of the electron is 1.602 into 10 power minus 19 coulomb. If you substitute all these values in this expression, then the value of lambda that comes out is 12.27 divided by root mu angstrom. So this is a direct formula for the de Broglie wavelength of an electron, and it is useful for us to calculate when you know the potential difference across which the electron is accelerated. Okay. So one point which is not here, but they will ask us, sometimes they'll ask you the graph between lambda and root v. So if you observe, lambda is inversely proportional to root v. So the graph will be a rectangular hyperbola like this. When they ask you to plot the graph between the de Broglie wavelength of an electron and square root of the potential difference that is being applied to accelerate the electrons, it will be a rectangular hyperbola. Okay. I hope it is clear, guys. So one important aspect to be noted, I've seen this as a common mistake. That's why I'm telling. This 12.27 will come in the numerator only if it is an electron. Suppose they ask you what is the de Broglie wavelength of a proton, it is not going to be 12.27. What is the reason for it?
Mass will be different.
The mass will be different, okay? So please be careful with it. If they ask something like this, you calculate and have the value ready. So mostly they will ask about electron only, if at all it comes. You read the question carefully. Okay. Next is wave mechanical concept of an atom. So listen, according to de Broglie's hypothesis, that is a theory that he has proposed, An electron of mass m in motion with a velocity v is associated with a wave whose wavelength is lambda, which is given by lambda is equal to h by mv. This we already know. So on the basis of de Broglie's hypothesis, an atom model was proposed in which the stationary orbits of Bohr's model were retained, but with the difference that the electron in various orbits behaves like a wave. So what they're trying to say is, you know the Bohr's quantization condition. So there are different models of atoms that were proposed. First, it started with Thomson's model, where it was plum pudding. That's what we are going to see in the next chapter. Or it's a watermelon model. Then came the Rutherford's model. Then came Bohr's model. So in Bohr's model, there is an important theory, point that he has given. Electrons will revolve only in those orbits where the angular momentum is quantized. That is, MBR is equal to nh by 2 pi. We have seen this expression in some other chapter also, where we saw Bohr magneton, that is magnetism chapter, right? So MBR will be equal to nh divided by 2 pi. So we are going to relate both. Remember, lambda is equal to h by mv is the de Broglie's wavelength of an electron. So we know that it was suggested that stationary orbits. What do you mean by stationary orbits? It is those orbits where the angular momentum is quantized, are those in which the orbital circumference is an integral multiple of de Broglie length. Okay, that is observed. If this is the radius, and if the electron is going to have wave nature associated with it, that is going to travel like a wave. Now, I'll mark certain red dots. Tell me, what is the distance? So, what is this distance between these two red dots? Think in terms of wave.
Wavelength.
This is one wavelength. Like this, how many such wavelengths do you have? 2, 3, 4, 5. In the diagram that I do, there are 6. What if there are n wavelengths associated? So can I say, if there are n wavelengths associated with it, that length mathematically should be equal to 2 pi r? Because 2 pi r is a circumference. So you're starting at this point, coming back to the same. So you're starting at the green point, coming back to the same point, within which there are n waves that are present. So n lambda is equal to 2 pi r. So look at the way I'm going to frame the equation. So when I write n lambda is equal to 2 pi r, n into the place of lambda, can I write it as h by mb is equal to 2 pi r. So nh is equal to 2 pi into mbr. Can I write it like this? But what is m into v into r, guys? So mbr is nothing but angular momentum. From this, can I write L will be equal to nh divided by 2 pi. And this is the condition for Bohr's quantization theory. So that's what we can see. MBR is equal to nh by 2 pi or L is equal to nh by 2 pi. So from equation 3, it is seen that the total angular momentum of the moving electron is an integral multiple of h by 2 pi. Thus, de Broglie's concept confirms the Bohr's postulate also.
So, can you scroll up?
This page?
Yes, sir. Thank you.
Okay. Done?
Minutes.
Yeah, right. See, actually, this part you can copy, the one which I've written here. Done?
Yes, sir.
Okay. So with this, we are done with the dual nature of matter also. So dual nature of radiation is over and dual nature of matter is also over. So there is one more concept, one last concept actually. So this, I can say it is a question. Okay, they'll ask you, what are all the reasons for which the wave theory failed to explain the photoelectric effect? Okay. Generally, if I have to speak in terms of marks, it is asked for a 3-mark. It is asked as a 3-mark question. So what you're supposed to write is, according to the wave nature of light. So from whatever we have discussed till now, there are certain conclusions that we are going to make. So according to the wave nature of light, the free electrons at the surface of the metal over which the beam of radiation falls, they absorb the energy, radiant energy continuously. Okay. So they are going to absorb the radiant energy continuously. Second, according to wave theory, the greater the intensity of radiation, the greater are the amplitude of electric and magnetic fields. Remember, I told you that intensity is directly proportional to amplitude square. This is what we used in wave theory, if you remember. So the greater the intensity, what will happen is, the greater will be the amplitude of the electric and the magnetic fields. Consequently, greater the intensity, greater should be the energy absorbed by each electron. So if greater energy is absorbed by each electron, then what should have happened to the kinetic energy of each electron? So try to connect the dots. I'm repeating it. According to wave theory, let's say there is a photosensitive plate, there is a light source which is there, which is having a greater intensity. Okay, means when it is here, let's say the light is falling on this surface. When I bring it close, I'm increasing the intensity of it. Now comes the question. So according to wave theory, what should have happened? If the intensity of this radiation is increased, then can I say that the amplitude of electric and magnetic fields will also increase, because light is an electromagnetic wave. It has electric and magnetic fields. So what should have happened when you increase the intensity? The electrons also should have absorbed greater amount of energy. If they have absorbed greater amount of energy, then the kinetic energy with which they are coming out should have varied. Am I right? So when the kinetic energy is going to vary, then the stopping potential should have also varied, because kinetic energy and stopping potential are related as EV naught is equal to half mv square, or mv max square, rather I can be more specific. So according to wave theory, if intensity increases, kinetic energy should have increased. If kinetic energy increases, stopping potential also should have increased with intensity. But what did the graph say? The stopping potential is independent of intensity, right? These graphs we saw, no? I1, I2, I3. Everything had the same stopping potential. So this is one of the places where wave theory failed. Okay. If this would have happened, then the concept of threshold frequency would have not arisen. So all these reasons say that wave theory couldn't explain the photoelectric emission. There is one more point also. According to wave theory, when the surface is absorbing energy continuously, then there should have been a time lag also, for which the electron is actually supposed to come out. But I told you there is an important point. In the laws of photoelectric emission, we saw that there is no time lag at all. I told you it is less than a nanosecond. When that is not there, again wave theory couldn't explain. So these are all the points due to which wave theory couldn't explain the photoelectric effect. So same points are there in your textbook also. You can just go through it. Okay. So with this, we are done with this chapter. Okay. So that's all about dual nature of matter and radiation. So in the next class, I will be starting atoms. That is maximum one class. Then again, nuclear and semiconductors. So maximum 4 to 5 classes, we should be done with the syllabus. So as I told you in the previous class, start studying. You will have tests. from the third week of November. So start studying. Okay. So I'll share this document with you guys. Is there any other doubt that you have?
No, sir.
Okay. So just wait for a minute. We'll wind up this session. Just wait.